Hello everyone, welcome to this talk on HPC best practices for deep learning. This is a collection of 10 tips based on my own experiences here at my time at Cambridge. Throughout the course of my PhD, I've researched application of deep learning for natural language processing. This presentation comprises things I wish I'd have known at the start of my time here, and there's a story behind every point in this presentation, whether either my time, quota, or unnecessary resources were used for these experiments. The high-performance computing facility here at Cambridge is a really useful tool when we need to use more resources than what you typically find on a laptop or on a desktop. You can request multiple machines to support a single experiment, which is useful for training large models, and it also allows you to run lots of experiments, potentially in parallel, that helps support things like hyperparameter search. This talk assumes that you already have some sort of basic familiarity with the HPC facilities here at Cambridge already. If you're new to this, then welcome. This presentation won't quite cover the basics. You'll probably find the Getting Started section on their website and their examples more helpful. But once you've got up and running, this tutorial will help you avoid some common pitfalls in your work. With great power comes great responsibility, and there's a lot of ways you can cause problems for yourself and for other people. This talk will address some of the ways you can make your experiments run more smoothly and get the best out of the facilities that the university have provided. Before I begin, I'd just like to reiterate that I'm not really an expert in HPC, but I've used the facilities a lot during my time here, and have probably made every mistake under the sun. This talk is a collection of learning points from my time here at Cambridge, and with seeing best practices at other places and other labs that I've interned at. While Cambridge has a certain configuration for their HPC, other labs may use different configurations, and to balance making this talk specific enough to be useful and general enough to support your time after Cambridge, I've made this tutorial a how not to tutorial with common pitfalls, rather than a how-to tutorial with specific advice. Another thing before we get started is that for this optional unit, you have to answer an attendance question, and the attendance question for this optional unit is, what is the name of the scheduler we use here at Cambridge? So at Cambridge, we have two classes of machine on the HPC cluster. There's login or head nodes and worker nodes. The login nodes are shared by multiple people. If you SSH into one of these and run the uptime command, you'll see that there could be somewhere between 50 and 100 people logged in at any one time. These are shared computers for managing your files and your scripts, etc., and submitting jobs. The two commands you're likely to use are sbatch for submitting a bash script to a worker, and sinter, and that's for starting an interactive session on a worker node. These submit work to a scheduler, and in the case of the Cambridge facilities, this scheduler is called Slurm. Other universities or labs might use different ones. When you run your jobs, you'll probably be allocated a worker node. For the lifetime of your job, you'll have dedicated access to the resources. And if you use a lot of resources there, you'll be fine. But if you use a lot of resources on the login nodes, you're probably going to give quite a few people a headache. So here's the first tip. Don't run work on the login nodes. There's a watchdog running on these servers, and I'm sure admins and other users won't take kindly to resource hogs. So how can we debug our code and our projects without having to wait a long time to join the queue? Well, thankfully, there's the interactive mode, where you can request resources to test your script. And if you use the QoS argument for quality of service, you can jump the queue and get dedicated access to a worker node for testing. You can use the same arguments as you would in your sbatch script submission, but this is traded off with a short time limit, and that currently is 1 hour. So that's suitable enough for testing, but not really suitable for running long jobs. On this slide, I've got a small example which you can look at later. Okay, so tip number 2, don't duplicate your scripts. When I first started using HPC, I had one script for running my project on my desktop and another one for running on the cluster. Then, as my project grew in complexity, I'd have different variants of the scripts with certain parameters or configurations I wanted to test. Things get very messy very fast if you do this, and it's likely that you won't be able to maintain it for long. The metadata you can see here defines how much resources your script requires, and it goes at the top of the bash file. You should notice that all of these are comments too, so a script that runs on Slurm will also work on your own machine okay. If you don't hard code things, your scripts should be portable across multiple platforms. However, If you do need to have different behaviors for different platforms, like any good computer scientist, it is helpful to apply the separation of concerns principle here. The key parts which are worth separating from your application are the environment and the configuration. The environment specifies which version of Python will be loaded, which libraries you'll use, and where the results will be saved. In contrast, the configuration will typically be things specific to your model, such as the model architecture, the number of epochs, and other hyperparameter choices. There's quite a few ways to do this, but an easy way to get started is to externalize the paths and allow these to be set, either through environment variables in Bash or through arguments you can pass to your script. If I need custom configuration or different behavior on Slurm, I write a very simple wrapper script to set up the directory for my experiments. Similarly, for configuration, while this could be passed as arguments in Bash, being able to read from a file will allow you to more easily reproduce or rerun your code. I pass in an argument to a configuration file, which is read by my script. Any arguments you pass to sbatch when you submit your job will also be passed directly to your script as bash arguments. This means it's very easy for you to reuse the same script for lots of different experiments. Inevitably, things go wrong when running your experiments on the cluster, so it's critical that your code can identify these failures early, fail safe, or recover from faults. The third tip is to do a test run before running a long experiment. There's nothing worse than pre-processing a dataset for an hour to find that the batch size is too big and you've run out of GPU memory. Similarly, I've also trained a model for hours upon end that crashed when the weights were saved after training was finished. If you can test every aspect of your code before you spend a lot of money on credits and sit around for a few hours, you'll be doing yourself a favor. The starting point is to make sure that things work locally before you even submit your job. Debugging on the cluster can be a bit of a pain, so if you can fix most of the faults locally before running your scripts, most of the faults you're likely to encounter on the cluster should be simple to diagnose and recover. Faults always happen when you least expect them and could occur in any part of your code, whether it's running out of GPU memory, having a missing file, or not being able to parse your dataset, checkpoints not being saved, or being corrupted upon saving. The key to a happy project is finding these faults early. You're going to want to run an end-to-end test run. Even before running your full experiment, you should be able to train your model, save your weights, load your weights from a path, make predictions, and report your results. Some of this can be done in software and the main script that runs your experiment. For example, frameworks such as Allen NLP or Hugging Face will run sanity check on a sample of data on the validation set before training. You can even write unit tests or test your code with continuous integration. But the best solution I found was just to run the entire script on a sample of a few hundred instances for a couple of epochs before training the full model. If your script fails on this simple smoke test, then it's a good indication that the full training won't work, and you'll save yourself a lot of time. You can use this to identify if your loss is converging, and whether you can make predictions with the weights that you save. I'd recommend having this as part of the same Slurm script you run your experiments with. That way, you won't forget to test when you update your code. The next tip I'd suggest is to save checkpoints regularly. A checkpoint is the state of your model and your optimizer, which can be saved to disk. Then, if for any reason your job crashes, you can resume this state at a later point in time. I'm not going to define how frequently you should be saving here. Setting this interval depends on your project. But I once had a project where I was working on which took about 12 hours per epoch during training. The library I used was configured only to evaluate and save the weights at the end of each epoch. If I wanted to pause training, or if there was a resource contention, I'd face a choice of having to wait a few hours until the next checkpoint, or losing a few hours of computation. Regularly checkpointing helps you limit the damage of unscheduled termination of your job. There's a lot of things that can go wrong on the cluster which may be outside of your control, such as running out of disk space, having the network file system go down, etc. All of these can be quite disruptive and mean that if your script isn't able to handle those events, you can be losing a few hours of work and struggle to work out which jobs completed okay and which ones need to be resubmitted or rerun. In other facilities, not at Cambridge, higher priority jobs submitted to the queue can cause low priority jobs to terminate. This is called preemption. Right before conference deadlines, the last thing you'd want is to struggle to retrain your entire model. Being able to save and load from checkpoints is a great time saver that would allow you to resubmit your job and resume from where you left off, assuming your code allows for it. The first thing you can do is to check if your code crashed. In Linux, processes return a non-zero exit code if something went wrong. This is returned as a special environment variable denoted by a question mark which will be 0 if the process was okay, or something else otherwise. The second way you can check to see if you need to resubmit your script is to listen for system interrupts. Interrupts are special messages that your code will need to handle, either in your bash script or in Python. For example, in Linux, a signal 9 interrupt is a message to kill the process. The scheduler can be configured to send a signal t seconds before your job runs out of time. This makes it really useful for making jobs which will run beyond the time limits that have been configured here at Cambridge. You can also manually send a signal with the scancel command too. Once you receive these signals, your code can do any action you deem appropriate, such as gracefully quitting or making a checkpoint. Once your job is terminated, you can resubmit it without having to recall sbatch using the scontrol command with your job ID. You can find more information about this in the docs. This next section will talk about making your jobs run faster, both reducing the time spent queuing and reducing the absolute runtime of your jobs. There's nothing worse than waiting around for hours for work to finish, or feeling like you're stuck in the queue for hours. For managing queue time, you need to choose the right service level and ask for the right resources. Most of the jobs you'll submit will either be submitted as SL2 or SL3. SL3 is a free service level, which offers a few thousand hours of HPC time per quarter. If you exceed this allowance, you'll get demoted to SL4, which has low priority. If you want a higher priority, you can pay a few pence per hour to use service level 2. SL2 jobs allow more resources and longer runtimes. However, if you exceed the limits set by the cluster, your job may not be accepted or could wait forever. Even though SL2 allows jobs to run for 36 hours, smaller jobs can be better. The scheduler will have to reserve time for the entire length of your job, so if you choose a shorter runtime, the scheduler will try and fit these smaller jobs in around larger jobs. If you request only what you need, your job may be run more quickly as the scheduler backfills the queue. Another aspect of the cluster is that Slurm has a fair share formula that prioritizes jobs based on how much you've used before. So if you're a heavier user, you may be waiting longer. The moral of the story here is don't be greedy. If your job isn't going anywhere, there probably isn't much point running it to completion. If you can terminate early, you'll be saving yourself credits as well as reducing the share of your CPU time on the cluster, meaning that you may get higher priority later if you need it. If you can manage checkpointing, resuming, and rescheduling, you might not need to submit 36-hour-long jobs either. But don't submit jobs that are too small. There's a lot of scheduling overhead that can slow down the cluster for other users. It's probably a bit pointless to run lots of small jobs if they each take less than an hour. Another cause for potential headaches is how you use persistent storage and access hard disks. If you run out of disk space, your jobs are going to crash. You do get a 10% grace over the storage quota for a few days, but don't rely on this for poor management of your working files. Firstly, don't save more than you need. For large models with millions or billions of parameters, each checkpoint that you save can be a few gigabytes. So if you've got a lot of experiments or are running models for a long time, you can easily eat up all of your hard disk quota. The first trick is to remove checkpoints after you finish training and testing the model. If you do really need to keep the checkpoints, it may only be worth keeping 1 or 2. You probably don't need to resume training or make predictions from every epoch in the model. If you are regularly saving checkpoints, don't save them too frequently. Disk access can be quite slow, and the time spent on saving the model state can eat into the time you'd spend training, meaning that your HPC balance spent on GPU will be used on other things. Choosing an appropriate checkpoint frequency is a balancing act, depending on the size of your model and the length of the training. Another mistake I've made before is using network disk for random access. This can happen when you don't fit your entire dataset to memory, or are using external resources such as document databases for training. The high latency of this meant that it would take about 20 to 30 minutes to load my entire dataset when using the network file system, whereas it would only take 2 to 3 minutes when testing on my local laptop. If you're finding that the network disk is too slow for your use, you can use the local scratch disks on the server. Each server has a few hard disks that are mounted to the /scratch directory. This is a shared resource and there's no guarantee there'll be free space on this drive, but using this for random access can have a lot lower latency than the network file system if you need it. Another common pitfall is to overwrite your experiments if you rerun your script. I've done this a few times before where I've had variants of my models that I wanted to test, and I forgot to update my model path and ended up deleting the model which I'd written half my paper about. A good way to prevent this is to use the Slurm job number in the directory name. This limits the blast radius to just one job. But it does mean that you need to find a better way to manage your jobs as you need to find a way to correspond which identity or which ID corresponds to the jobs and experiments you're running. To save time when loading your dataset, another quick tip is to cache your features to disk. If each of your instances takes a long time for pre-processing, such as tokenization, it's probably best to compute this all just once. Caching your features can save time and mean that you spend a high proportion of your job training the model rather than doing housekeeping. Finally, after your experiments have finished training, you need to think about how to manage your assets. The HPC work folder you get has fast access and 1 terabyte of storage, but this isn't backed up. While you can do everything you can to mitigate data loss in your scripts, you still can't guarantee that other factors beyond your control won't result in losing critical files. On the cluster, your user folder only has 40 gigabytes, but it is backed up with hourly snapshots and can serve as a good place to save your important findings. Once you've got experiments working on HPC, the next step is to make sure you can reproduce them and make sure others can use your code and make sure you can get these results into your paper or into your thesis. To start with, there's nothing worse than having different versions of your code giving you different results and not knowing what you've changed that caused the performance or accuracy to vary. A good way to prevent this from happening is to only use code that is managed in Git to run your experiments. This way, you can always connect your results to an exact version of your code. In your code, you should be able to log which Git branch, tag, or commit hash is the one that your code is based on. You can use a library such as GitPython to access this info, or as part of your bash script, you can use the Git program to output which commit hash you're using to a file. In addition to logging which version of your code you're using, you should also log which libraries you're using. There's plenty of papers showing that different versions of Torch or NumPy can result in changes in model accuracy or may introduce breaking API changes that mean your code will no longer work. To stop this from happening, saving the exact version of what libraries you're using in a requirements file can help other people, or even your future self, reproduce your experiments. You can dump which pip packages you're using with all associated versions by using the pip freeze command. In the same vein, logging everything you can will help you identify what caused errors and contributed to your results. One of the easiest things you can change is to call bash with the -x flag. This flag will echo all commands back to you, and these will get picked up with the log file that Slurm saves. Saving all hyperparameter choices and model configuration choices into a file which you can use later will help you reuse the same configuration when replicating results. And finally, for debugging, you can log things like GPU status before you start training, just in case there's any problems you need to raise to the HPC admins or diagnose if your model is running out of memory. It's best to log these all the time, because by the time you're fault finding, reproducing it and understanding what contributed to your fault becomes a real challenge. I've wasted countless hours running experiments which don't train very well, or which quickly overfitted the training data. To understand whether your hyperparameter choices are appropriate and whether your model is diverging, logging the loss and accuracy regularly to a file can help you identify and track whether your model is working as you'd expect. There are many open source or web-based tools, such as TensorBoard, Visdom, and Weights and Balances, which can help visualize which hyperparameter choices are appropriate. A final sanity check, which can save you a lot of time when debugging, is also to print a sample of the features to a file, validating whether the pre-processing is working as you'd expect. I recommend doing this all the time for a sample of instances, even before you start debugging, so that you can quickly verify whether tokenization is working properly, whether your inputs are being truncated, or whether you're missing key data. One thing that I alluded to at the start of this talk is that the parallelism the high-performance computing cluster offers you can help you with hyperparameter and model search. There's a couple more tips on how you can make this easier for yourself too. Firstly, one of the ways you can mess up on the cluster is by spamming it with lots of individual jobs and small tasks. You'll probably see emails like this after new, fresh-faced researchers submit thousands of tasks programmatically. But each task is individually scheduled and it has a high resource overhead on the cluster. Not to mention that submitting jobs programmatically can be rate limited and take longer than you'd expect. This can make it harder for other people to submit their jobs to the queue too, as you're effectively performing a denial of service attack. So here's tip number 9. Don't spam the scheduler. Rather than submitting one job for each hyperparameter choice, use array jobs instead. Slurm and most other schedulers support array jobs. Array jobs are one job, but with many parts. For example, calling sbatch with the -- array 1 to 1000 will create a job with 1000 parts, and you can access the ID of the part with an environment variable. This means that you no longer need to call the scheduler programmatically, and as a rule of thumb, if you're programmatically calling the scheduler to submit jobs, you're probably doing it wrong and likely to get an email like the one I showed earlier. The final point is don't manually search for hyperparameters. Do it programmatically. This helps reduce your bias and saves you a bunch of time waiting for jobs to finish. This isn't really a new problem, and if you look around, there's countless frameworks that do model optimization for you, which you can download and integrate into your project. Performing things like grid search is fairly easy for you to do yourself if you want to, but I'd suggest using open source projects as people who have already been through the pain and have hard-coded all the edge cases you're likely to encounter. Furthermore, after you've performed all your experiments and have got your results, don't make mistakes when copying the numbers into your thesis or paper. See if you can dump a CSV file into a preformatted LaTeX or generate a preformatted LaTeX table as part of the model output. Furthermore, after you've performed all your experiments and have your results, don't make mistakes when copying the numbers into your thesis or paper. See if you can dump a CSV file or print a preformatted LaTeX table as part of your model output. This will save you a few headaches, and as tools such as Overleaf support Git and have APIs for file management, you can probably find clever ways to push results directly into your paper. I've been through quite a lot of tips and thought I'd like to end on a non-technical point too, with a final bonus point. Don't work late. Most of the mistakes I've made on HPC are when I was rushing to submit jobs just before midnight because I wanted results in the morning for a supervisor meeting. There's nothing worse than staying up late, making sure training is okay, debugging at 2 a.m, or waking up to find that your experiment has crashed about 1 hour in. The queue is often quieter in the mornings, so if you submit then, you should be able to react to errors during normal working hours, supporting your own well-being. Thanks for watching. I hope this has been helpful. I've put all the slides for this up on my website, and I'll continue adding to these as I continue to develop my approach and research methodology using HPC. Hope it helps, and feel free to email me if you have any questions.